PH Next Generation Seminar Series is a networking event for early career scholars, junior modelers, and epidemiologists working on or interested in mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série de séminaires MFPH Next Generation est un événement pour les chercheurs en début de carrière, les modélisateurs juniors, les épidémiologistes travaillant ou intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the Fees Institute operates for thousands of years. It has been traditional land of Huron-Wendat, Seneca, the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Churchill Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Fields opère depuis des milliers d'années. C'est la terre traditionnelle des Huron-Wendat, des Sénèques et des Mississaugas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de tout Churchill Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Our guest today is Dr. Jingjing Chu. She is a postdoc fellow at York University studying the mechanism of emerging infectious diseases intervention strategies using multivariant models. She holds a PhD from Western University in applied mathematics, and she was a postdoctoral fellow at the University of Alberta, where she was investigating modeling of the spread of chronic wasting disease in wild mule deer populations in Alberta and predicting cyanobacterial bloom. Notre invitée aujourd'hui est la docteure Jingjing Chu. Elle est postdoctorante à l'Université de York, étudie les mécanismes des maladies infectieuses émergentes et les stratégies d'intervention à l'aide de modèles multivariants. Elle est titulaire d'un doctorat en mathématiques appliquées de Western University et elle a été postdoctorante à l'Université d'Alberta. Elle a étudié la modélisation de la propagation d'encéphalopathie des cervidés dans la population des cerfs mulets sauvages de l'Alberta et la prédiction de la prolifération de cyanobactéries. Her talk will be today on modeling the effects of travel-related policies on disease control and meta-population structure. Sa présentation aujourd'hui portera sur la modélisation de l'effet des politiques liées au voyage sur le contrôle des maladies dans une structure de métapopulation. Thank you very much for accepting our invitation, and the floor is yours.
Good afternoon, everyone. Thank you very much for inviting me to this talk. And then I hope everyone has been enjoying some warm weather. I don't know why recently the weather is like summer, and then hopefully everyone's having some time off and then enjoy some leisure time. And what I'm going to talk today is kind of related to the to traveling. Just that, and let me try and share my screen. Can see my screen, right?
Yes.
Okay, great. So this is a joint work with my lab mate Jen Wang and my postdoc supervisor Saeed Mokhtas at York University. We work on the modeling of COVID-19, and there are different topics in our lab. I focus on the kind of metapopulation model. So talking about the traveling, so I believe we are all in Canada. So after more than 3 years into COVID, have you think about traveling? I don't know. I have been thinking about traveling. Maybe some of you would want to travel to a warmer country and then enjoy some beach and then or some interesting events or nice foods in other places. But in the same time, when we are traveling, we cannot avoid thinking about traveling with virus or the possibility of bringing virus or bacteria or other antigen to other places. That's the thing. We have to consider how to manage or control the extent of the spread of disease. So this is kind of overview of what I'm going to talk about now. Okay. Now, in general, emerging infectious disease often have a potential for global spread. Not every disease, but usually as a development of air transportation, we can predict that in the near future, many times, once there's one spot in the Earth anywhere, that there is a possibility for the disease to go across the continents and to other countries. And our global air transportation system can be thought of as a network of nodes connected by air services offered by the airlines. And interestingly, the International Air Transport Association, the IATA, has kind of a report. They have data showing the international connectivity. They found that for the top 10, they actually studied a lot of countries. I just put the top 10 countries, which are most connected by airlines. The growth over a decade is like between 54% to over 153%. That's a lot. That means we cannot ignore the possibility of future risk of more emerging infectious disease over different countries. And then we through air travel and transportation, we should look into how do we implement several travel policies. And we already see that there are examples such as about 20 years ago, the original one, the SARS, the severe acute respiratory syndrome, has spread from mainland China to other places. But that was it didn't last very long. But the influenza is another infectious disease we have seen spreading many years, right? And then comes the 2019 COVID. Those are all the airborne diseases. And to deal with those kind of severe public health problems, many intervention and restrictive measures have been implemented globally. For example, we all know that at the beginning of the pandemic, between different countries, there are kind of different ways to control the spread. For example, from the very strict ones, for example, the travel ban from and to affected regions, and some countries have screening and self-reporting at the international airports, and also, of course, the quarantine and testing. When look at the local scale, we have those within population control measures. For example, we have limited indoor meeting, right? And we limit the number of social events, and we kind of reduce the percent of available seats in cinemas. And also for group sports, we limit it under maybe 20 people. And then indoor dining has also been reduced. And also we all have vaccines, and I believe most of us have 2 or 3 or even 4 vaccines already. And in the near future, we will going to have maybe yearly vaccine. I think vaccination is a very good way. If the COVID vaccine could be combined with the flu vaccine, that will be perfect. And the thing we don't want to look at, we don't want to happen is lockdown, right? That is a bad thing because that will affect the economy and also impact the social and mental health of everyone. So the thing is, for some country, they don't want to cut down their connection with other countries because maybe their economy rely on tourism, and they want the tourists to come, but they cannot ignore the threat of the emerging infectious disease. That's why we will need to look at the travel policies. What is the effective travel policy? For example, as a traveler, if I have 1 or 2 weeks of vacation, I would not want to spend 5 or 6 days in a hotel before I can go and enjoy my vacation time, right? So that's why we are going to try to build a meta population framework to evaluate different travel policies. For example, in our study here, we consider 2 communities or 2 populations or 2 patches. We use those terms interchangeably because it's in a general sense. So 2 populations, and then they will be traveling, and along with traveling, there will be infections traveling along with people. And after traveling, people are required to quarantine. And also, maybe they are combined with a testing policy after the quarantine. And then the testing and quarantine is not like a perfect one, right? They are always leaking. We call this leaking because of false negative rate when people getting out of quarantine, right? You cannot let people stay in the hotel for two weeks, right? That's when statistically you believe the virus or all the potential as asymptomatic cases will go away, but that's not realistic for travelers. So for a shorter quarantine, combined with testing or not, there will be possibility for the infected people to get mixed with a target or destination, people in the destination of their vacation. And then that will lead to the future outbreak in the second or our population B. Of course, there will be traveling back, but the thing is, we think the initial infection happens in population A, and then we here in our model, we will not consider the travel-related restriction when people are traveling from patch B to patch A. So we have this idea and we want to build the model. We first look at the within patch dynamics, and we started with 5 basic components. The first one, of course, is based on the SEIR model, and we have a component here, which is IA. The little I here means isolation. And I wanted to say that we have 2 concepts here. One is isolation, the other is quarantine. There's a difference between them. For the isolation, we will say that's when people get a positive test. They kind of confirm that they have the disease, and then they we call it the isolation. But the quarantine for our model is like we're not sure if people are infected or not, so we put them in the hotel and for a fixed time of quarantine, and then figure out if they are infected or not. So quarantine people may have been infected, but they haven't been confirmed by a test. But here, the isolation, we have like here, there's a square over this unlucky person, and then this is isolation. And then in our model, there's something interesting here is we have this proportion of infected individuals who are tested. We think about that in this way. There's exposed people, and after a while, it will progress into the infected state. There's alpha EA, but we think once they are going to be infected, there is a proportion of people which is indicated by the eta. This is a proportion of infectious individuals who will go and take a test. Maybe this is something impacted by what's the proportion of the symptoms people are showing, and also it is based on how many test kits are available, right? Like how much the public health has invested into the system so that people have access to get the test. So this eta is something we would like to check later. So this is a basic within patch dynamics. Okay, and then one thing is that without travel, we will assume patch A and B would have the same dynamic if they have been introduced, a disease has been introduced into their system. And this C here is a sensitivity of test for the infectious individuals, meaning that even if a person is theoretically or they are actually infected, but the testing with technique may not be able to detect all the infected person. So that's why we have a sensitivity of test for the infected individual. Okay, now that we are clear about what is the dynamics within the patches or within the populations, now we want to think about what's going to happen if we allow people to travel from patch A to patch B and come back. And also, we have the starting point here, the 5 components within patch dynamics for each patch. And then we start to allow people to travel. Those little flights are indicating those people are going to be able to travel, or those people can travel, because this capital I, little ia is isolated, so those people are not going to be allowed to travel. And we think about a strategy that everyone want to travel needs to take a test. And then because the testing has a false negative rate, there's a little proportion for the exposed people to be able to travel, but a proportion of them will be isolated. They will be detected by the testing. So that's what's going to happen with EA. And for IA, those people are infected. They are also going to take a test, and a big proportion of them is going to be isolated. But still, there is a false negative rate, right? And those people will also be able to get on the plane and then travel. But before those people are able to get mixed with the population in patch B, they are required to get in to a hotel and then quarantine for a fixed number of time. For here, we are going to think about just 1 day or 2 days or 3 days. Those are very short time because we think about what the tourists will feel about the duration of quarantine, right? I as a traveler will not be happy if I have to quarantine for a really long time. And also, of course, the SA and RA are also able to travel. And then they are going to take tests, but nobody will have the virus, and they will always have a negative test result, right? And the interesting thing happened inside the quarantine is that if a person entered the quarantine as exposed, there is a possibility for this person to develop symptoms or become infected during their stay in the hotel. That's something require us to consider carefully, because this will involve some kind of distributed delay. So for those 3 compartments, they are able to, some of them will be able to recover, right? And some of them will be detected by the testing after quarantine. But some of them, like the red arrow has shown, they're going to leak into the population. The EQB, they will be mixed with EB, like they are join the EB population in patch B and mixed with the patch B population. So that's how, like, traveling, even with travel restrictions or testing or quarantine, is going to bring the disease from one patch to another. This is how we consider the model. And for people in this patch B, we also consider there's a rate for people to travel to patch A. And here, I think we can zoom in a little bit here. Here are some parameters here that we have a travel rate between populations, and we're going to set them to equal value. And then there's a sensitivity also for infectious individuals. Compared with the sensitivity of tests for exposed individuals, this number, the CI will be larger. And then the sigma 1 is kind of a switch parameter for testing travelers from patch A to B before departure. And there's a sigma 2 parameter. It is a switch parameter for testing travelers at exit from quarantine in PB. So from this figure, we can think about there are 2 testing is possible to happen. Like, this is a quarantine, right? Before quarantine and before traveling, there's a possibility to take a test. And after quarantine, at here, when people are exiting the quarantine, there's another testing. Okay, and we have this tau, the duration of quarantine upon travel in PB. So we can control how many days we ask people to stay in hotel. And now that we have this framework diagram, and we're going to look at the model. So starting with the patch A, we have 6 compartments because in addition to SEIR, we have we have the isolation for the exposed and isolation for the infected. And then we have the traveling from A and from B to A, right? Those are travelers. Everybody except those who are isolated will be able to travel. And also, if we look at here, this is EA. Those are the people who exit their latent period. A proportion of people will take a test at the rate eta, and the positive rate is per C. So that's why this is a proportion of people who who either didn't take the test or they took the test but have a negative result, and they join the infected population. They don't have to be isolated, but there's a proportion here. Let me change the pointer. There is a proportion of people who are infected. They change their status from EA to I, but they are quarantined, like here. And then what's happened here for the delta part? The delta A is the rate of traveling for EA. Now, before traveling, there is a testing, and we have this testing. Switch, sigma 1, and then once they get tested, there's a sensitivity of the test. So those people, even though they want to travel, they're detected by the test. So they go from EA to EIA. Yeah. And like these two parts are not able to travel, so they don't have the delta A or delta B. That's for the patch A. Now we look at the quarantine. So this is where the interesting thing happened, because from the patch A equations, the 6 equations here, we don't see any delay, right? But when we look at the quarantine upon arrival, we have to think about the delay, how delay happens, because we have this fixed duration of quarantine, okay? And this is the I people, they are leaving this patch A, and some of them has joined the isolation because they have a positive test, and those people who are not tested, who are not detected, will be able to get in the plane and get a quarantine, right? They are at the hotel, and at time t, the rate of increase of this component is this rate is instantaneous, depends on t. And of course, this is the recovery rate. The interesting thing is here in this term, it has a kind of delay here because we have a fixed duration of quarantine, how days. So that's why it's like those people has entered this I state quarantine tau unit time ago, or tau days ago, and after tau days, a proportion has recovered, so they're not going to be infecting patch B population. And people who are still able to infect other people, the number of them has already reduced by this factor. That is because the delay effect. Okay, similar thing happens to the exposed person, but a little bit different is some people who are exposed, like I mentioned before, they can change their state within the duration. And once they change their state within the duration, within the quarantine, it's not a fixed delay. It becomes a distributed one. So it will involve some kind of an integral here, like here. We rewrite this term using this g of t function. If you're interested how this is developed, I can explain it in the end. So that is for patch A and the quarantine. Here comes the patch B. Also in patch B, we have 6 components, S, E, I, R, and also the isolated E and isolated I. And the different thing is here, because we have this dispersal. Remember, everyone needs to quarantine after they're traveling. So that's why we have the delta A, SA, and this is T minus tau. So those people arrived at patch B tau unit time ago, and then they after tau days, they are out of their quarantine. Even if they take a test, they'll never get a positive result, because we assume there will not be false positive rate. So this is for S, and also similar for the recovered. Those are simple ones. And in between, we have those leaky terms. Those are the ones I explained in the previous slides. Those are the leaking because of either people are not showing symptom or not yet recovered, but after a quarantine, there is still a small rate for people to for the test to give a false negative result. And this there's a capital G of t function we introduced to convert the distributed delay into a constant delay. And then it's actually a kind of in this form, but we want it to be in the differential equation model. So we kind of convert it into this way and express other integral terms by this g of t. This is a kind of a standard way if our model have a distributed delay, we introduce an additional variable to deal with distributed delay, because constant delay will be easier to analyze. Now that we have the model, this is the model diagram simplified, and we're going to use simulations to investigate different scenarios of control. And as a starting point, our key parameter beta is actually estimated from other parameters, and when we assume R naught is 2.38. That's a number from a literature. And then we work backwards, like we assume the latent period to be 2.5 and the infectious period to be 5.5. And this eta, remember, is the proportion of people who get tested when they become infected. And we change this within this range. And this CI is the sensitivity of the test for the infected people. The test sensitivity is better than the exposed because they're more, the virus load is higher in the infected people. And you can see the exposed people has a really low positive rate. And this delta A is this 10 to the point to 10 to -4 per day. And our initial population for patch A and patch B are both 100,000. And our initial infection, we assume it to be in population A, and the starting infection happens here. The EA has 10 people. And then, yeah, this work has been submitted, and we have submitted our revision. So a lot of things will be online soon, hopefully. And our goal is actually, let me change the point here. So we have this eta, we have this range, because this is a kind of related to control measures, because if you invest more money in the testing kit, people can have more easier access to the testing kit. Maybe more people would like to test, and that will help the control. The other thing is the tau as maybe a decision maker in population B. I wanted, like, I need to decide how do we help people more. Is it going to be like introducing a lot of people into the population for tourism, for economic reason, but kind of sacrificing people's health? No, that's not the good thing, right? I need to make the decision whether we will want people to quarantine for 1 day or 2 days or 3 days. And the other thing, maybe here, there are 2 switch parameters here for testing before traveling and after quarantine. Those are the places that we can control whether we want to test or not. So, yeah, this is the starting point. And then here are some results. First one, we look at the testing within each population. This is the testing before traveling, right? Everyone going to traveling needs to take a test. And we look at the incidence of infection in the absence of quarantine upon arrival, PB. So if this depends on the sigma-1 parameter, and we set the sigma-2 parameter always equals 0. And for example, this is a 1. This is time from 0 to 500 days. Different colors are for different proportion of people getting tested when they become infected. This show how increasing the probability will help improve or delay the peak of the infection in PA, sorry. Yeah, we are varying the eta. And here, under the same condition, without testing before travel, population B, you see, this is a peak here for this one, but it's around 70 days, right? And this is in PB. It's like this is how the peak of outbreak in population B is delayed. Those are the different scenarios, and this is with testing before traveling. So people are requested to get tested. A lot of infected people will be isolated. They're not allowed to travel. And a small portion of exposed people will also be detected. So they are not allowed to travel. But there are still some people going to travel, but not as much because we have this testing before travel. That's why if we compare this point here with this one, you can see kind of this peak has been delayed in population B, right? Okay, this is the second one. This is the incidence of population B with quarantine of travelers upon arrival. And we look at the effect of quarantine and exit testing. So we have this category, we have the testing at exit. So after the quarantine, people want to travel, and then they get on the plane, get off the plane, and they are staying in a hotel. After a fixed number of days, they're required to get a test or not. Those are two scenarios. And the other way, here is duration of quarantine. We have 3 possibilities: 1 day, 2 days, and 3 days. Now we are also looking at the incidence. So those are like different testing rate, and also the solid and dashed lines correspond to scenarios without and with testing before departure from PA. So that's why the solid one is with testing, right? Sorry, the solid one is without testing. The solid one is without testing, so that's why the peak is earlier. And then we can see that, for example, with testing, it can actually delay the peak. I mean, notice this all of this plot is for population B, and we introduced the infection in population A by setting E of A to 10 people, right? Since that time, the population B, for example, when testing rate is 0.5, we found that the peak of the outbreak in population B is around 300 days. That is without asking people to test after before they leave their hotel, right? Once we have test implemented, we found that this is delayed around by around 30 days. So the thing is, beside this, when we compare across here, we actually found that 1 day, 2 day, or 3 days quarantine didn't make a really significant difference between the peak in B. But the testing or not can make some difference. For example, in this scenario, there are 30 days difference. And this is the second result. And the third result is when we compare across the quarantine strategies, we actually look at one scenario, which is 1-day quarantine combined with testing before exiting of quarantine. And we look at 3-day quarantine without testing. And we actually found that the shorter quarantine with test will outperform the longer day quarantine. So the solid line here is 1 day plus test. The dashed line is 3 days with no testing. So that this is a good news. Why? Because think about if you are the public health agent worker, and you want to tell people or tell the government whether we need to ask people to stay really long, or we can allow people to stay in hotel for just 1 day, but we ask them to have a test. They will actually be more effective than letting people to stay in a hotel for 3 days. So this is something interesting. Here's a summary. Remember at the beginning we were thinking about this story, like if I want to travel between countries, but there are viruses coming with me, and how many days should I stay in hotel, or whether I should combine the quarantine with testing? Are they equally effective, or which ones is more effective? That's the question. To solve the question, we build a meta-population model, and then we consider the testing and quarantine. And also, with this framework, we compare different scenarios of control measures, and the most interesting result is that we found that 1 day quarantine plus testing before exit quarantine can outperform and 3-day quarantine without testing at exit. So that's an interesting thing. And for the future work, actually, we could consider a kind of symmetric scenario when both group of people will need to quarantine after traveling. And also because we have considered the population size of the patch A and B to be equal to each other. That's a simplified assumption. We can actually consider different scenario with larger population size in one population and smaller in another. And in addition, we actually can have a larger network of traveling, right? We have multiple countries or multiple continents. We consider the connection between those continents and how can we collaborate together to avoid the spread of disease without implementing lockdown or travel ban. Yeah, this is a page for the leaky quarantine, but maybe if you have questions, I can explain it to you. But here's the end of the talk, and I thank you so much for your interest in my talk, and I thank my lab mates and supervisor for helping me to complete this research. Yeah, thank you very much.
Thank you very much. For the people who missed the beginning of the talk, it will be posted on the field channel on YouTube.